Welcome to the deep dive.
Yeah.
You are probably listening right now looking for that specific aha moment without drowning in a bunch of information overload.
Right. Getting straight to the good stuff.
Exactly. And today's topic, it delivers exactly that. Imagine sending a microscopic wireless charger directly into a severed spinal cord.
Which already sounds like science fiction.
It totally does. But it goes in, fuses with your body's own stem cells, and then it just waits. It waits for a command from a magnet outside your body. And once activated, it actually teaches your paralyzed nerves how to grow again.
Yeah, it's a massive shift in how we approach this kind of trauma.
Because normally, when you think about a severe injury, like something you or a loved one might experience, say a broken arm or a really deep cut, there's this comforting expectation.
Right. The body knows what to do.
Yeah. The doctor sets the bone, your body bridges the gap with calcium, and your skin just, knits itself back together.
But the spinal cord, it absolutely does not follow those rules.
No, it doesn't. When a spinal cord is severed, that whole self-repairing machinery just halts. Instead of healing, the body kind of panics.
It does. It forms this dense, fibrous barrier. We call it a glial scar.
Right, and that scar physically blocks new nerve fibers from growing, right?
Yeah.
It creates this hostile, totally impenetrable environment.
It's a profound biological bottleneck. For decades, the medical field has essentially tried to force a solution using, well, relatively blunt instruments.
What did those older modern therapies even look like?
So previous modern therapies tried bridging that gap by implanting stem cells directly into the spinal cord and then using electrical stimulation to encourage those cells to grow through the scar tissue.
Which, the underlying logic makes sense. You give the transplanted cells a little electrical nudge to wake them up and get them to work.
The logic is completely sound, but the execution has historically been highly invasive.
Because of the wires, right?
Yeah, exactly. To deliver that electrical stimulation, surgeons physically had to implant permanent electrodes and run cables right alongside the spinal cord.
And the spinal cord is one of the most delicate structures in the human anatomy.
Right. So you have the sheer physical trauma of introducing this bulky hardware, and the resulting inflammation, well, it often just caused the transplanted stem cells to die before they could ever integrate.
Wow. Okay, let's unpack this because that is where our mission for today really begins. We are exploring a groundbreaking June 2026 paper published in Nature Materials by researchers at ETH Zurich.
Yes, an incredibly fascinating paper.
And we are going to look at how these scientists figured out a way to ditch the physical cables and the implanted electrodes entirely.
Which changes everything.
It really does. By combining living stem cells with magnetoelectric nanoparticles, they're creating what they call biohybrid microrobots that actually repair severed spinal cords.
Yeah, but to understand how we can avoid those invasive electrodes, we first have to really understand the microscopic robots doing the work.
The researchers call them NPC bots. Right. Let's start with the biological half. What exactly is an NPC?
Right, so the living component is a neural progenitor cell, or NPC, and these are derived from induced pluripotent stem cells.
The iPS cells.
Exactly.
So just for a quick biology refresher for you listening, iPS cells are essentially regular adult cells, like the skin cells on your arm.
Yep, just normal body cells.
And scientists take them into a lab and they reprogram them, right? They rewind the cell's developmental clock, giving it back its stem cell superpowers so it can become almost any type of cell in the nervous system.
That's spot on. That reprogrammed cell is the biological engine. It's primed to become healthy nerve tissue.
But just dropping them in isn't enough.
No, because,
Okay, 2 layers.
yeah, the inner layer responds physically to external magnetic fields, and the outer layer acts as a translator, essentially converting that magnetic response into electrical signals.
Oh, this is where that microscopic wireless charging pad analogy comes to mind.
I love that analogy. It's very accurate.
Because, when you set your phone on a charging pad, an electromagnetic field safely passes through the plastic case and creates an electrical charge inside the battery.
Exactly the same principle here.
So the nanoparticle picks up a magnetic signal from outside the patient's body and turns it into a localized electrical shock just for that single cell.
Right, and it's so elegant. The magnetic field passes harmlessly through the human tissue, hits the inner core of the nanoparticle, and makes it vibrate or deform slightly.
And the outer layer feels that vibration.
Yes, the outer shell is made of this piezoceramic material. It experiences that mechanical stress and instantly converts it into an electrical voltage.
Wow. But wait, I have a pushback question here. If we are injecting thousands of these tiny, independent electric generators into the swirling fluid of the spine, how do we ensure the cells actually stay attached to the nanoparticles?
That is the big engineering challenge.
Right, because I imagine they could just wash away from each other before they even reach the injury site.
You're entirely right. Relying on chance encounters inside the body is impossible. So
Uh,
they solved this by pre-assembling the NPC bots before they ever enter a syringe.
oh, so they build them first.
Yeah, in a highly controlled environment called a lab on a chip.
Which brings us right to the manufacturing side. Because knowing what a 6-micrometer MPC bot is only matters if we actually know how on Earth researchers build them.
Exact.
And more importantly, how they can build enough of them for future medical use, right? Because making a handful in a lab won't help you if you're paralyzed in a hospital.
Right. So Professor Salvador Panay-Vidal engineered this amazing fabrication process. It all happens on a specialized surface that measures just 1 square centimeter.
Just 1 centimeter. That's tiny.
Very tiny. Cells are trapped in a central microreservoir, then the nanoparticles are injected in, and within just 30 minutes they bind together to form the NPC bots.
But how does a metal particle safely latch onto a living, delicate stem cell?
It's all about highly calculated fluid dynamics and electrostatic affinity.
Okay, break that down for me.
So the microchamber on the chip creates these specific fluid vortexes. They gently force the cells and nanoparticles to collide at the exact right speed and angle.
Because if they hit too hard,
The cell membrane ruptures and the cell dies.
and if they hit too softly.
They just bounce right off each other.
Oh, I see.
But at the perfect velocity, the natural electrostatic charges on the cell's surface interact with the nanoparticles coating. They just adhere naturally without any damage to the cell's biology.
Here's where it gets really interesting, though, because scaling this up from a tiny 1 centimeter chip to actual clinical viability seems impossible. Lead author Hao Ye explained they need huge numbers, right?
Massive numbers. You need hundreds of thousands of microrobots just for basic cell studies.
Right. And to scale up to animal experiments, or eventually humans, we are talking millions of these bots per patient.
Yes, millions. And you can't just take the ingredients from that 1 centimeter chip and dump them into a giant 100-liter vat.
And because you'd lose the fluid dynamics.
Exactly. The moment you increase the volume, you destroy those delicate vortexes. The cells would literally be crushed by the physical forces of a larger fluid environment.
So let me challenge you on this. Is running a bunch of 1 centimeter chips side by side truly a feasible long-term manufacturing step for global clinical use?
Yeah.
Or is this just a stopgap for the lab until they invent a new machine?
Hao Ye makes a compelling case that it is the long-term strategy. The plan is to scale out, not scale up.
Scale out.
Yeah. Instead of building bigger vats, you print thousands of these inexpensive 1 centimeter chips and you operate them in parallel.
Oh, like server racks.
Exactly like server racks in a data center.
Yeah.
You have a facility filled with these tiny chips running simultaneously. Every batch gets the exact same perfect microscopic fluid dynamics, but the parallel operation gives you the macroscopic output you need for humans.
Wow, okay, so we have the biology, the nanoparticles, the microfactories to build millions of them. That moves us to the ultimate test, right? Putting them into injured living creatures to see if they actually reverse the irreversible.
Right, the animal trials. This was collaborative work with Stefan Neuhaus and Jingjing Zhang at the University of Zurich, and they started with zebrafish larvae.
Which makes sense. Zebrafish are great for watching cellular development in real time.
Yep. So they injected the NPC bots precisely into the injury site of zebrafish with severed spinal cords and exposed them to an electromagnetic field.
And what happened?
In just 3 days, the fish exhibited nearly normal swimming and exploratory behavior.
3 days. That is staggering.
Mm-hmm.
But, a fish is a fish. The mouse miracle is what really caught my eye.
Yes, testing on mice with completely severed spinal cords.
Because unlike zebrafish, a mouse spinal cord does not naturally regenerate at all.
No, it's a permanent injury, just like in humans.
Yet, after 28 days of this treatment, their nerve cells had actually reconnected.
Physically bridged the gap.
The results in the paper were incredible. The mice had improved gait, their stride length increased, they got their coordination back, and they resumed exploratory behavior.
What's fascinating here is exactly why this worked so well compared to older methods.
Right, because of the scar tissue.
Exactly. It comes down to the minimally invasive nature of the tech. We talked about how cutting into the spine to implant electrodes causes more inflammation.
Which causes more scarring.
Right. But here, the magnetic fields easily penetrate the tissue from the outside. So there are no cables or implanted electrodes touching the highly sensitive spinal cord.
And the frequency and strength of that magnet can just be adjusted externally, right?
Completely dynamically, yes, without a single extra surgery.
So we've seen this incredible healing in mice. But to move this into human hospitals, for you or me, we have to answer two huge questions. First, what happens to the bots after the spine is healed? And second, where else in the body can we use this?
The safety aspect is crucial. Because once the stem cells differentiate into nerve cells, the NPC bots are designed to essentially dissolve into the tissue.
Which sounds a little scary, right? Having metal nanoparticles dissolve in your spine.
It does, but they expect them to be stable and minimally reactive because the nanoparticles have a specific barium titanate coating.
Barium titanate.
Yeah, it's a highly stable piezoceramic shell. It acts as a biocompatible shield so the inert metals don't leak out while the bot is working.
But they still need to do future research on this, right?
Absolutely. Scientists must determine exactly whether and how these particles are degraded or excreted by the body over the long term. Like, do the liver and kidneys safely filter them out years later? We need to know that.
Definitely. And before human trials, there's another hurdle.
Right, mapping the exact magnetic fields for humans.
Because a human torso is a lot thicker than a mouse.
A lot thicker, yeah. They have to figure out exactly which magnetic frequencies penetrate best and determine the optimal duration for the stimulation in humans.
Now, Professor Panay Vidal didn't just stop at spinal cords. Because this lab-on-a-chip platform is so reproducible and scalable, it has massive implications for other fields, specifically cardiology and oncology.
Oh, absolutely. The vision is far broader than spinal injuries. It can be adapted to make treatments safer, more controllable, and vastly more effective in targeted regenerative therapies.
So what does this all mean? Let's theorize for a second. If we can use remote-controlled cellular robots to bridge a severed spine, could we theoretically use them to rebuild a damaged heart tissue after a severe heart attack?
Yes. Following a myocardial infarction, you get dead muscle and fibrous scar tissue in the heart, which leads to arrhythmias.
Right.
Theoretically, you could create NPC bots loaded with cardiac progenitor cells instead of neural ones, inject them into the dead zone of the heart, and use an external magnet to stimulate them.
So they would mature into healthy beating heart muscle.
And act as a microscopic distributed pacemaker from the inside out.
Oh, wow, a cellular pacemaker. But wait, what about oncology? Because in cancer, you want to destroy tissue, not regenerate it. Could you guide these bots to electrically disrupt tumor growth?
Exactly. It flips from regeneration to disruption. Certain aggressive cancer cells are highly sensitive to specific electrical frequencies that mess with how they divide and multiply.
So instead of whole-body chemotherapy,
You deploy a microscopic Trojan horse, guide the bots into the tumor, apply the magnetic field, and command them to release localized electricity that paralyzes the tumor's ability to grow.
sparing all the healthy tissue around it.
Exactly.
Wow. Okay, we have covered some incredible territory today. Let me just concisely recap this journey. We started with the devastating permanent reality of a severed spinal cord. We saw how researchers engineered a 6-micrometer bot on a 1-centimeter ship and then mass-produced them using parallel chips.
A huge engineering feat.
Truly. Then they cured paralyzed mice using external magnets, and now we are looking at a scalable future where this exact tech might rebuild hearts and dismantle cancer tumors.
If we connect this to the bigger picture, the true breakthrough here isn't just the cure itself, it is the method.
Remote control aspect.
Exactly. Proving that we can seamlessly merge nanotechnology, stem cells, and external magnetic fields to safely command human biology without a single incision.
It is profound, and it leaves us with a final thought to really mull over. For decades, we've thought of robots in medicine as these clunky metal machines performing surgery from the outside. But if the future of robotics is invisible, it's made partially of our own reprogrammed cells and it just dissolves into our tissue when the job is done, at what point does the machine end and the human begin?
Yeah, that is the question.
And building on that, if our cells become highly tuned receivers waiting for electromagnetic frequencies to heal us, will our artificially enhanced biology eventually pick up unintended signals from our modern, noisy world?
Oh, that's a wild thought.
Right. Will the medicine of the future require us to install biological firewalls just to safely walk down the street? Something to think about as this tech scales. Thank you so much for joining us on this deep dive. And as always, keep questioning the world around you.